Hi, my name is Seon. I'm 17 years old and a research intern at Professor Alan Asper-Guzik's lab at the University of Toronto. Currently in the fields of machine learning and chemistry, graph convolutional networks and chemical fingerprints are the predominant approaches for representing molecules for property prediction. However, in recent years, natural language processing models and transformers have become the de facto standard for representation learning tasks, thanks to their strong downstream task transferability. And so in this work, we aim to be one of the first attempts to systemically evaluate transformers on molecular property prediction tasks via our ChemBERTa model. We show that ChemBERTa scales incredibly well by adding increments to the pre-training dataset size, offering competitive downstream performance on the MoleculeNet benchmark suite, and also offering useful attention-based visualization modalities of molecules. Our results suggest that transformers offer an incredible, promising avenue of future work in molecular representation learning and property prediction. And to help facilitate these efforts, we released a curated dataset of 77 million smiles of molecular string representation from PubChem, suitable for large-scale self-supervised pre-training. Molecular property prediction has seen a bright recent resurgence thanks to the success of graph convolutional networks on various benchmark tasks. However, data remains an incredibly fundamental challenge for supervised learning in a domain where each new labeled data point requires costly and time-consuming laboratory testing. And so determining effective methods that use large amounts of unlabeled sequence-based structured data remains an important unsolved challenge in the field. And so given the availability of millions of these smile strings, transformers offer an interesting alternative to both expert-crafted and GCN learned frameworks and fingerprints. In particular, the math language modeling task, commonly used by BERT-style architectures, is incredibly analogous to pre-training tasks using graph settings, such as atom masking. Moreover, since molecular modern transformers are engineered to scale on massive amounts of NLP corpora, they offer practical advantages over GCNs in terms of efficiency. Currently in the field of pre-training on molecules, the most emergent and popular method remains graph pre-training strategies. Graph pre-training strategies currently for molecules include predicting masked atom nodes in a molecular graph, or aiming to try to get a model to map nodes with a similar surrounding structure to nearby embeddings. Unfortunately, building robust pre-training strategies with molecular graphs is a problem that still remains to be unsolved. And so we aim to see if natural language processing-based pre-training tasks using a pre-training procedure from RoBERTa, which masks 15% of each token on an input string, works as a means to fundamentally learn a chemical space. Our hypothesis is that, in learning to recover masked tokens, the model forms a representational topology of chemical space that should generalize well to property prediction tasks. And so for pre-training, we curated a dataset of over 77 million smiles molecules from PubChem. And we released over 15 pre-trained ChemBERTa models on the Hugging Face Model Hub. And these models have collectively generated over 30,000 inference API calls so far. We use the popular ChemProp library by Original Barzolet's group for all the baselines. We benchmark the model on a message parsing network, random forests, and support vector machines. We see that ChemBERTa performs state-of-the-art on the TOX21 task on the ROC-AUC metric. The TOX21 task is a toxicity prediction dataset of over 7,831 data points. For each dataset, we generated an 80-10-10 train validation test split using a scaffold splitter, which aims to create chemically distinct train and test splits. And on the MoleculeNet task we evaluated, ChemBERTa approaches, but still doesn't yet beat nearly every single competitive baseline set by the ChemProp model. But what we do find to be incredibly interesting is as we increase the pre-training dataset size, we see strong boost to the downstream performance. Notably, what we see is that on average, ChemBERTa scales incredibly well with more pre-training data. When you scale ChemBERTa from pre-training on 100,000 smile strings to 10 million smile strings, we see an average boost of over 11% in ROC-AUC across all four benchmarking datasets, and we also see an average of 6% boost on the PRC-AUC metric. These results suggest that ChemBERTa learns more robust representations with additional data and is able to leverage this information when learning downstream tasks by exploring more and more of the chemical space. In addition, we use BERTviz to inspect the attention heads of ChemBERTa. On TOX21, we found that certain neurons in the ChemBERTa model learned chemically relevant functional groups and aromatic rings. We also observed that other neurons that track bracket closures, a finding which is in keeping with results seen in attention-based recurrent neural networks, which show the ability to track nested parentheses. Our ChemBERTa model frequently refers to similar chemical substructures in each smile strings with a higher attention weightage, as well as similar sets of smiles grammar, such as bracket openings and closures, which represent side branches in a molecule. What's really cool about this is that by visualizing things such as aromatic rings, the model learns features that are vital to drug-like molecules, as aromatic rings are a key feature in more stable drugs. We contrast this with molecular graph-based attention, in which we see how attention applied to molecular graphs highlights very many different chemical functional groups, such as hexagonal benzene structures, as well as aromaticity as well. We also ensure the open sourcing of all of our models and utilities for using our models through the DeepChem project, a decentralized framework for using machine learning for drug discovery started at the Pandey Lab at Stanford. And so we build multiple utilities for using large-scale language models, notably ChemBERTa, and many different utilities for molecular tasks, such as toxicity classification, protein ligand binding, and property prediction. Finally, we see that in our current analysis, we only cover a small portion of the total hypothesis space we hope to eventually explore. We've only tested our pre-training approach on 10 million molecules, which is a small fraction of the total chemical space. And so we hope to apply this mass language modeling pre-training to even larger data sets of 77 million and up to 230 million molecules, in which we hope to see similar boosts to benchmarking on fine-tuning datasets. We also hope to do more fine hyperparameter tuning, as well as introducing more chemically induced relevant pre-training tasks, such as taking the embeddings of the transformer and feeding them to a node-based structure, utilizing the novel benefits of a molecular graph representation for downstream benchmarking. Thank you for listening to my talk, and if you have any questions about this work or machine learning and chemistry, I'd be happy to take them. Thank you.